Welcome to the Power Electronics class. Myself B. Veernarayana, Senior Assistant Professor, Department of Electrical and Electronics Engineering. I am going to deal the subject Power Electronics. Course outcomes of this course. After the end of this course, the students will be able to explain the different types of power semiconductor devices and their characteristics. Course outcome 2, distinguish the differences between the single phase and three phase controlled converters. And CO3, analyze the operation of single phase AC voltage controllers and cycloconverters. Course outcome 4, analyze the operation of different types of DC to DC converters or choppers. And CO5, illustrate the operation of inverters and application of PWM techniques. The course contents of this course, here we have total 5 units. Unit 1 covers power semiconductor devices. Unit 2 covers AC to DC converters. Unit 3 covers AC to AC regulators and cycloconverters. Unit 4 covers DC to DC converters, and Unit 5 covers DC to AC converters. The prerequisite to this power electronics course is basic electrical engineering and circuit theory, which I already learned in the previous semesters, basic electrical engineering and circuit theory. The textbooks of this power electronics, the power electronic circuits, devices and applications by Mohammad Rashid. Another textbook was Power Electronics by Dr. P.S. Bimra, Kanna Publishers. Coming to the first unit, power semiconductor devices. The unit outcomes, after this end of this unit, the student will be able to, first unit outcome 1, explain the different types of power semiconductor devices and their characteristics. Unit outcome 2, explain the turn on and turn off methods of SCR. Unit outcome 3, design the protection circuit for the SCR. The contents of the first unit, characteristics of power MOSFET and power IGBT, theory of operation of SCR, static characteristics or steady state characteristics, dynamic characteristics of the SCR, 2 transistor model, turn on and turn off methods of the SCR, snubber circuit design, basic requirements of gating circuits for SCR, IGBT and MOSFET, and finally operation of triac and static VI characteristics of triac. So first we go through the first module, classification and characteristics of power semiconductor devices. Learning outcome, at the end of this lecture, students will be able to explain the classification of different types of power semiconductor devices and their characteristics. First we go through the introduction to the power electronics. Here, power electronics is one of the contemporary subjects of electrical engineering, which has seen a lot of advancement in recent times. Even though in our daily life we are using the different types of the power electronic devices, even though without knowledge of those devices. So here the power electronics is the combination of power engineering and electronics engineering. If you go through the power engineering, here we concentrate how the power should be generated, transmitted, distributed and utilization of electrical energy. On the other hand, the electronics engineering is mainly concentrate on power semiconductor devices, how effectively you use those power electronics devices and you convert one form of energy into the another form. The components which works are available in the power engineering mainly works on the principle of Faraday's laws of electromagnetic induction, whereas the components present in the electronics engineering which works on the principle of movement of holes and the electrons. So here We have different types of the power electronic devices. All the power electronic devices are acts like a switch. If you go through the switch, we have two states or two modes of the switch. Those are either off state or on state. If you go through the off state of the switch, it consisting, there was some voltage is available across the switch and there is no current flow through the switch, that is open circuit. Hence why here we take the current is here the current is taken as 0 and you have some voltage across the switch when the switch will be in the off state. And if you go through the another state of the switch, on state simply acts as the closed circuit or short circuit. When the switch will be in the on state, you have some current flow through the switch and the voltage across the switch is 0. The voltage across the switch is transmitted to the device which connects across the switch. These are the two fundamentals in power electronic devices. All these power electronic devices acts like a switch and it has two modes, on state and off state. And if you go through the block diagram of the power electronic system, it consisting, here we have main source, power electric circuit, load, sensors which are used for the feedback, and here we have control unit, reference or input, and it is firing circuit. So if you go through this control unit will receive the signal from these sensors. The sensors will sense the actual voltage or actual current available across the load. The parameter should be sensed by using these sensors and the output of the sensors is given to the control unit. In this control unit, it is compared with the reference input by using the comparator and that error signal is given to the control unit and this control unit will generate the control signals which are reduce the error and that control signal is given to the firing circuit. Depends on the output of the control unit, this firing circuit will generate the pulses to these switches present in the power electric circuit. So corresponding that this power electronic circuit is operated and desired output voltage to the load can be fulfilled by using this power electric circuit. And here we have the main source means we have different types of the sources like AC source and the DC source, and AC sources are again classified in two types, single phase AC supply and the three phase AC supply. Depends on the availability of the source and depends on the load requirement, we will design the different types of the power electronic circuits. Those are mainly we have 5 types of power electronic circuits, each having different purpose. Depends upon the load point of view and depends upon the availability of the source, we will consider the any one of these power electronic circuits. First you go through the rectifiers. These are used to convert AC to DC. If you have the AC source, I just want to convert that AC source into the DC, then simply we go through the rectifiers. So these are rectifiers are used to convert fixed AC to variable DC. If you have the output is variable DC from the fixed AC input, those are called phase controlled converters or controlled rectifiers. If you have fixed DC output voltage as the output from fixed AC input, that is called uncontrolled converter. So we clearly discuss what is the controlled rectifier and what is the uncontrolled rectifier in the second unit. And choppers, which converts fixed DC to variable DC. Fixed DC to variable DC. The choppers are going to discuss in the fourth unit. And inverters, these converts DC to AC, which is having the variable voltage and variable frequency. So if we have the DC source as the input and I just want to collect the AC output voltage, then we will design the power electronic circuit like an inverter, which converts DC voltage into a AC voltage at a desired voltage and desired frequency. These inverters are going to studied in the fifth unit. voltage regulators or AC voltage controllers. These are used to convert fixed AC voltage to variable AC voltage without changing the frequency. And last one, cycloconverters. These are the converters which converts power at one frequency to power at variable frequency without changing the magnitude. If you go through the voltage regulators, here we will change the voltage level, but frequency must be maintained constant. If you go through the cycloconverters, here we will change the voltage is maintained constant, but the frequency level should be changes. So these AC voltage regulators and cycloconverters together are discussed in the third unit. And coming to the first unit, power semiconductor devices. Based on the VI characteristics, gate signal requirement and degree of controllability, the power semiconductor devices are mainly classified into three types. Those are uncontrollable devices, controllable devices, and semi-controllable devices. First we go through the uncontrollable devices. If you go through the uncontrollable devices, the turn on and the turn off of these devices are not under the control. They should simply depends on the nature of the supply. So if for any devices, the turn on and the turn off of the devices are not under the control, those are simply called the uncontrollable devices. Example for the uncontrollable devices like diodes. Here this is the symbolic representation of the diode, and the terminals of the diodes are anode and the cathode. If you go through the ideal diode, when you made anode is made positive with respect to the cathode, then the diode is said to be in the forward biasing mode, which is considered as the on state of the diode. And if you go through the same diode, in the next case, here we have anode, here we have cathode. We just reverse the biasing of this diode. Here anode is made negative with respect to the cathode. Then the diode is in the reverse biasing mode. So simply here we will treat the diode will be in the off state. So when the anode is made positive and cathode is made negative, then it is considered as the on state of the diode. If you go through the reverse biasing mode, anode is made negative with respect to the cathode, then the diode is said to be in the reverse biasing mode, which treat the off state of the diode. So the on and off states of the devices are depends on the source. So those are not under the control. Whenever you make positive anode and cathode is connected to the negative, it automatically comes to the on state. When anode is made negative and cathode is made positive, it automatically comes to the off state. So those on and off states of these devices are not under the control. They simply depends on the source. Hence why those are called the uncontrollable devices. Best example, diodes. Second, if you go through the controllable devices, in these controllable devices, the turn on and the turn off of these devices are not under the control. The turn on and the turn off of these devices are under the control. The example for these controllable devices are transistors. We will discuss what are the different types of the transistors will be discussed. And last one, semi-controllable devices. The turn on of these devices are under the control, but the turn off of these devices are not under the control. Those are simply called the semi-controllable devices. So here the turn on of these devices are under the control, but the turn off is not under the control. It should simply depends on the nature of the source. The best example for these semi-controllable devices are thyristors. So why these are called the semi-controllable devices, what are the thyristors will be discussed in this class. So coming to these transistors, in 1947, J. Burden and W. Bretarian and Shortley invented the transistors. So mainly the transistors are classified into four types. If we go through the applications of these transistors, those are used in integrated circuits. And transistors are mainly classified into 4 types. Those are BJTs, bipolar junction transistors, MOSFET, metal oxide semiconductor field effect transistor, IGBT, insulated gate bipolar transistor, and SITs, static induction transistors. So in our curriculum we have BJT, MOSFET and IGBT. So we are concentrate on these 3 transistors. First we go through this BJT. The BJT is termed as a bipolar junction transistor. The BJT names as bipolar junction transistor. So it is a 3-layer, 3-terminal, 2-junction power semiconductor device. It is a 3-layer, 3-terminal, 2-junction power semiconductor device. So if you go through this structure of this BJT, depends upon the construction, the BJTs are mainly classified into 2 types, either NPN transistors or PNP transistor. And these BJTs are current controlled devices. The BJTs are current controlled devices. The BJT bipolar junction, the bipolar means that conduction should be takes place in the BJT due to the movement of both holes and the electrons. If you go through this NPN transistor, if you want to design the NPN transistor, one P-type semiconductor is sandwiched by the 2 N-type semiconductors. If you want to design the P-type NPN transistor, here one P-type semiconducting material is sandwiched by the 2 N-type semiconductors, then we will design the NPN transistor. Here 3 terminals means the outer N terminal is called emitter, outer N terminal is called collector, and middle P terminal is called the base. Here the 2 junctions means here it is the J1 and it is the junction J2. So it is a 3-layer NPN, 3 terminals, emitter, base and the collector, 2 junctions J1 and J2. And if you want to design the PNP transistor, here one N-type semiconductor is sandwiched by the 2 P-type semiconductors, that is PNP transistor. The outer 2 P layers are simply called emitter and the collector, and the middle base region is simply called base. If you go through the symbolic representation of the NPN transistor, here it is the symbolic representation of NPN transistor. Here the arrowhead on this emitter depends on the arrow direction on the emitter. We are going to identify whether it is the NPN transistor or PNP transistor. If the current direction is towards to the emitter, then it is considered as the NPN transistor. And if the current flow through the emitter is away from the emitter, then that is treated as the PNP transistor. In power electronic circuits, mostly we prefer this NPN transistor over the PNP transistor. So if you go through this NPN bipolar junction transistor, so in this NPN transistor, the name itself, one P-type semiconductor is sandwiched by the 2 N-type semiconductors. And this is the circuit diagram which is used to analyze the steady state characteristics of the NPN transistor. Here, if this current flows towards to the emitter, that is the NPN transistor symbolically. Here these are the biasing voltages which is provided across the base and the emitter and the collector and the emitter. This is the biasing voltages, and here it is the voltage across emitter and base terminals, and this is the current flow through the emitter. Out of these 3 terminals, here you have base, emitter and the collector. If you go through this NPN transistor, we have the 3 different configurations or 3 different arrangements, like common emitter configuration, common base configuration and common collector configuration. So if you go through this common emitter configuration, these are used for high voltage and high current gain applications. And if you go through the common base, these are used for high voltage and low current gain applications. And if you go through this common collector, these are used for low voltage and high current gain applications. So most of these power electric circuits we have, if you go through the common emitter configuration, we are able to collect the high voltage gain and high current applications. So here we go with common emitter configuration. So out of these three terminals in common emitter configuration, this emitter terminal should act as the input terminal. This base terminal is acts as the input terminal, common emitter. So this emitter should act as common to the both input and the output, and this collector terminal is considered as the output terminal. So here this NPN or PNP transistors are current control devices. So if you go through the common emitter configuration, here the input terminal is base terminal. So here the base current is the control signal, and collector current is the output current. Collector current is the output current, and this emitter is common for both input and the output. So if you go through these input characteristics of the NPN transistor, these input characteristics simply shows the relation between input current and input voltage. So we already consider for common emitter configuration, base is taken as the input terminal. So here the current flow through the base terminal, it is considered as the input current, and voltage across the emitter and base terminals, here voltage across the base and emitter terminals is taken as the input voltage. If you draw the characteristics between input current and the input voltage, those simply gives the input characteristics of the NPN transistor. If you go through these input characteristics, here this collector emitter voltage is the variable parameter or controllable parameter. So if you observe these input characteristics of the NPN transistor, this resembles like a diode VI characteristics. Diode VI characteristics means whenever you made anode is positive with respect to the cathode, whenever the voltage across the diode crossovers the threshold voltage or break-in voltage, then the current flow through the diode should be increases. See here, up to this, if you have the collector emitter voltage is 0, up to this threshold voltage, there is no base current. Okay, corresponding that transistor is in the off state. Whenever this voltage across this base emitter junction crossovers this voltage, then the base current should be raises. So these input characteristics are similar to the forward biased PN diode, PN junction diode. So here if you increase the collector base, here the collector base increases, corresponding that collector current is also increases. And coming to the output characteristics of the NPN transistor, these output characteristics simply shows the relation between output current and output voltage. So here the collector terminal is taken as the output terminal. So the current flow through the collector is taken as the output current, and voltage across collector and the emitter terminals is taken as the output voltage. Here the base current is the control signal. Here base current is the control signal. So if you draw the characteristics between collector current and collector emitter voltage, this simply gives the output characteristics of the BJT. Here these output characteristics of the BJTs are mainly classified into three regions. Those are, first one is the saturation region, and this is the second region which is considered as the active region, and third one, this one is cutoff region. Cutoff region. So if you go through this saturation region, the initial part of this output curve is linearly increases with respect to the voltage. So that portion is simply considered as the saturation region. In that saturation region, the BJT operates like a switch. And here, if you go through this active region, the collector current is constant irrespective of the voltage across collector and emitter terminals. So this region is called active region. In that active region, the BJT operates like an amplifier, current amplifier. So here these are the different output characteristics for different types of the base currents. If you increase the base current, corresponding that the collector current is also increases. And this cutoff region, for safe and reliable operation of the BJT, we will never meet into the cutoff region. So these are the different operating regions of the NPN transistor. Next, you go through the second classification of the transistor, MOSFET, metal oxide semiconductor field effect transistor. And if you go through these MOSFETs, these are the unipolar devices. Whereas if you go through the BJTs, those are bipolar devices. Bipolar means the conduction should be taken place through the BJTs due to the movement of both holes and the electrons. Whereas if you go through these MOSFETs are unipolar devices. Unipolar means the conduction should be taken place due to the movement of majority charge carriers only. If you go through these MOSFETs, depends on the construction point of view, MOSFETs are mainly classified into two types. Those are depletion type MOSFETs and enhancement type MOSFETs. And depends upon the majority charge carriers, both the depletion type MOSFETs and enhancement type MOSFETs are further classified into two types. Those are N-channel depletion type MOSFET or N-channel enhancement type MOSFET and P-channel depletion type MOSFET or P-channel enhancement type MOSFET. If you go through the N-channel depletion type MOSFET, here the majority charge carriers are electrons. If you go through the P-channel depletion type MOSFET, here the majority charge carriers are holes. And most of the cases for switching applications, we go through the N-channel enhancement type MOSFET. N-channel enhancement type MOSFET. And the MOSFET consisting three terminals, those are source, drain and gate terminal. Source, drain and the gate. So if you go through the structure of this N-channel enhancement type MOSFETs or N-channel depletion type MOSFET, if you go through the N-channel depletion type MOSFET, here we have P-type substrate is taken as the main surface. On this P-type substrate, two heavily doped N plus regions are diffused onto the P-type substrate. Here these two heavily doped substrates should act as the drain terminal, another one acts as the source terminal. And this P-channel substrate should act as the gate. Here the three terminals, drain, source and the gate. And if you go through the P-channel depletion type MOSFET, on N-type substrate, two heavily doped P plus regions are diffused. Here the two outer P regions should act as drain and the source terminals, and this terminal should act as the gate. These are the symbolic representations of depletion type MOSFETs. So if you go through this N-channel depletion type MOSFET, this arrow indicates, depends upon the arrow. If this arrow is towards to the junction, that is simply considered as N-channel depletion type MOSFET. If this arrowhead is away from the junction, that is considered as P-channel depletion type MOSFET. And identification of enhancement type MOSFETs and depletion type MOSFETs, if there is physical contact between the drain and the source terminals, those are called depletion type MOSFETs. See here. Here we have physical contact between the drain and the source terminals. Between the drain and the source, here you have the physical contact. Then those are called depletion type MOSFET. If you go through the enhancement type MOSFET, then the symbolic representation for this N channel enhancement type MOSFET like this. So if you go through this difference between these, this is enhancement type MOSFET. So if you go through this enhancement, there is no physical contact between the drain and the source. Then that is the N channel enhancement type MOSFET. And here you have the physical contact like this between drain and the source terminals. This is N channel depletion type MOSFET. So if you go through this N channel depletion type MOSFET, here the majority charge carriers are electrons and minority charge carriers are holes. This is the simple structure of this N channel depletion type MOSFET. And if you go through this operation, whenever we provide the positive voltage across the gate and the source terminals, we provide the voltage across gate and source terminals, that is simply gate biasing voltage. As long as that gate biasing voltage is 0, then there is no conduction takes place between the drain and the source terminals. If you made to increase the voltage across gate and source terminals, corresponding that, here we have the silicon dioxide layer. Below the silicon dioxide layer, the electrons will be accumulated. If you keep on increasing the voltage across gate and source terminals, corresponding that the number of electrons accumulated behind the silicon dioxide layer is also increases. At particular level, that current should be flows from drain to the source terminals, depends upon the gate and source voltage. So here the MOSFET is termed as the voltage controlled device, and here the control parameter is gate and source voltage. So if you go through these transfer characteristics, here if you draw the characteristics between the drain voltage and the gate source voltage, here the gate source voltage is considered as the input voltage and the drain current is the output current. And if you draw the characteristics between the drain current and the gate source voltage, those are simply considered as the transfer characteristics of the MOSFET. Here, as long as the voltage across gate source terminals is below the threshold voltage, there is no drain current. That means if you keep on increasing the voltage across gate and source terminals, corresponding that the number of electrons accumulated below the silicon dioxide layer is increases. That electrons will be sufficient to brought that MOSFET into the on state whenever the voltage across the gate and source terminals cross over the threshold voltage. After this threshold voltage, the drain current should be increases. So at this point we will treat that MOSFET comes to the on state. So those characteristics simply represents the transfer characteristics of the MOSFET. And if you go through the output characteristics of the MOSFET, this shows the relation between the output current and output voltage. For this MOSFET, we have the three terminals, drain, source and the gate. Here source is the common for input and output terminal. Gate is the input terminal and drain is the output terminal. If the voltage available across drain and source terminals is considered as the output voltage and the current flow through the drain terminal is the output current. So if you want to draw the output characteristics, this will shows the relation between drain current and the drain source voltage across drain and source terminals. Here the output characteristics are further classified into three types or three regions. Those are ohmic region, this one, saturation region and cutoff region. Cutoff region means this one. This one is the cutoff region. So if you go through this ohmic region, in this ohmic region the MOSFET operates like a switch. The MOSFET operates like a switch. And in the saturation region, Here the current flow through the output terminal is constant. Here these are the output characteristics for different controllable voltages. Here the controllable voltages is gate source voltage. If you keep on increasing the voltage across gate source terminals, corresponding that the drain current is also increases. So after this ohmic region, the MOSFET comes into the saturation region. Here the drain current is constant irrespective to the voltage across drain and source terminals. That saturation region simply treats as the amplifying mode of the MOSFET. Amplifying mode of the MOSFET. And last one, cutoff region. For safe and reliable operation of the MOSFET, we never enter into the cutoff region. If you go through this cutoff region, drastically the current flow through the drain terminal is increases and the MOSFET may goes to the damage. That is the simple output characteristics of MOSFET. If you go through the comparison between BJT and the MOSFET, here the BJT is a bipolar device. That means the conduction should be taken place due to the movement of both poles and the electrons, and here MOSFET is the unipolar device. The conduction should be taken place due to the majority charge carriers only, and it is a current controlled device, whereas in MOSFET is the voltage controlled device. Here the output is controlled by controlling the base current for common emitter configuration, whereas in MOSFET the output voltage is controlled by considering the voltage across gate and source terminals, are simply considered as the gate voltage. It has negative temperature coefficient, so the parallel operation of this BJT is difficult. Negative temperature coefficient means if you increase the current flow through that BJT, corresponding that the resistance offered by that BJT is decreases. If the resistance is decreases, the current flow through the BJT is increases. Whenever the current flow through the BJT exceeds its rated value, then the BJT may goes to the damage. Hence why, due to this negative temperature coefficient, the parallel operation of these BJTs are difficult. So you need some current limiting resistors must be required in case of the parallel operation of the BJT. But if you go through this MOSFET, it has the positive temperature coefficient, so the parallel operation of these MOSFETs is very easy over the BJTs. And the drive circuit is complex, whereas in drive circuits in the MOSFET is simple. One more important difference, here you have the low conduction losses and high switching losses. The BJTs have low conduction losses and high switching losses, whereas in MOSFETs high conduction losses and here you have the low switching losses. And these are used in high power applications, whereas in MOSFETs are used in low power applications. And these BJTs have high voltages and low current ratings, whereas MOSFETs have the low voltage and high current ratings. If you go through these BJTs, the switching frequency is very low over the MOSFETs, and these MOSFETs are used for high frequency applications, and these are the symbolic representations of the NPN transistor and PNP transistor. Here it is N channel enhancement type MOSFET and it is the P channel enhancement type MOSFET. These are the differences between BJT and the MOSFET. The third classification of the transistors was IGBTs, insulated gate bipolar transistor. So if you go through the BJTs and the MOSFET, we have some advantages in the BJT and we have some good qualities in the MOSFET. If you go through these good qualities of the BJT has low conduction losses and the MOSFET has low switching losses, and the parallel operation of this BJT is very easy and the parallel operation of the BJT is difficult and the parallel operation of the MOSFETs are very easy, and these MOSFETs are used for high frequency applications and these BJTs are used for high rating applications, high voltage and high rating applications. So what are the good qualities of the BJTs and the MOSFETs should be considered, and you design the new power electronic device, that is nothing but IGBT. So this IGBT is relatively new device in power electronics which possess the better qualities of both BJTs and MOSFET. And this BJT had the properties, the input properties like MOSFET and the output properties like BJT. Why? Because the MOSFET has low switching losses. So the input characteristics of the IGBT simply possess the MOSFET, and BJT has low conduction losses. Hence why the output characteristics of the IGBT are designed depends on the BJT. Hence why this IGBT has the input characteristics like MOSFET and output characteristics like BJT. And this IGBT is also a voltage controlled device. Why? Because it is the input characteristics like MOSFET na. So MOSFET is voltage controlled device. So the IGBT is also a voltage controlled device. So if you go through this symbolic representation of the IGBT here, this is the symbolic representation of the IGBT. It is designed by combining the best qualities of both MOSFET and BJT. Here the terminals of IGBTs are gate, emitter and the collector. The three terminals of these IGBTs are gate, emitter and the collector, and this is the symbolic representation of IGBT. This IGBT is sometimes also called as metal oxide insulated gate transistor like MOS, IGT, or gain modulated field effect transistor, JMFET, or conductively modulated field effect transistor, COMFET, or insulated gate transistor, IGT. So if you go through the structure and working of the IGBT, this is the cross-sectional view of this IGBT. It has the two junctions J1 and J2 and 4 layers P, N, P and the N. The outer P layer is simply called the injection layer. The outer P-type substrate layer is called injection layer. Above the P-type region, this is called the drift region. So this is called drift layer and this is the injection layer, and this P is body layer. On these two heavily doped N plus layers, we will connect the emitter terminal, and the outer P-type substrate or injection layer is connected to the collector terminal, and here you have the gate on this P-type substrate. That is a simple structure of the IGBT. Coming to the working of the IGBT, here these are the biasing voltages, gate biasing voltage and this is the collector biasing voltage. Initially if you gate is made positive with respect to the emitter and this gate voltage is 0 initially, then this positive terminal of this collector voltage is connected to the P-type substrate, hence why this junction J2 comes to the forward biasing mode. The junction J2 comes to the forward biasing mode and this junction J1 is in the reverse biasing mode. Hence why as long as the gate emitter voltage is 0, that IGBT is in the non-conduction state, that is simply off state of the IGBT. If you increase the voltage across gate and source terminals, corresponding that the electrons must be accumulated below this silicon dioxide layer. This is the silicon dioxide layer. Below this silicon dioxide layer, if you keep on increase the voltage across gate and source terminals, corresponding that the negative charge carriers will be formed below the silicon dioxide layer. At particular level, these electrons will be moved towards to the collector terminal, corresponding that the current will be flows to the collector to the emitter. Whenever the current is established in the collector terminal, then we will treat the IGBT is in the off state. IGBT is in the off state. So if you go through these characters types of IGBT, the IGBTs depends upon the structure. IGBTs are mainly classified into two types. If in the construction of the IGBT, if you have the N plus layer, which is buffer layer, is present, that is called punch through IGBTs or asymmetrical IGBTs. And in the construction, if you don't have the N plus layer or buffer layer, those are called non-punch through IGBTs or symmetrical IGBTs. N plus layer, buffer layer should be present here. If you have between this N minus layer and this P layer, if you have the buffer layer, then those IGBTs are called punch through IGBTs or asymmetrical IGBTs. And if you don't have the buffer layer in the structure of the IGBTs, those are called non-punch through IGBTs or symmetrical IGBTs. The main difference in symmetrical IGBTs and asymmetrical IGBTs, if you go through the symmetrical IGBTs, those have equal forward and reverse breakdown voltages. If you have the different reverse breakdown voltage and forward breakdown voltages, those are simply called the asymmetrical IGBTs. Depends upon the application point of view, we will consider either punch through IGBTs or non-punch through IGBTs. Here, the symmetrical IGBTs are mostly used in AC circuits, whereas the asymmetrical IGBTs are used in DC circuits. Like if you go through the phase control rectifiers, then if you have the AC source as the input, then we prefer the asymmetrical IGBTs, and if you have the DC circuits as the input, then we will prefer the symmetrical IGBTs. And the applications of IGBTs, these IGBTs are used in various applications like uninterruptible power supplies or high voltage DC transmissions or for traction systems. For different types of the applications, we prefer these IGBTs.